Okay, we'll take a brief look at what is the generalization of free groups. What are free objects? Okay, so the free group was not really within the category of groups, because we also looked at sets and the underlying set. So that's what's called a concrete category. It's like a set with a structure, but we don't need to say the category is built in such a way. Instead, we have a category C, and then we have a functor, okay, which maybe I'll use this funny S for it, which will map C to set. That is, for each object we have a category. Of course, you could just map everything to the trivial set or something like that and get a functor, but we don't want that. We want this to be what is called faithful. Okay. What this means is the following. Suppose I take AB inside the category. Okay. Then if I look at morphisms from it in the category C of AB, so this maps to morphisms of in the category set of S of A, S of B. This funny S, I should say, S of B. So the underlying set of A and underlying set of B, this has to be 1, 1. So this is injective. Okay. Now, just intuitively, we are looking at, for example, topological spaces and looking at their underlying sets. What this is saying is a continuous function is a function, and different functions, if you have two continuous functions, if they are different as continuous functions, they are different as functions itself. Okay, so there is a restriction on what are functions, but no additional structure. So this is exactly the setting we have with set, topological spaces, groups, even sets themselves mapping to themselves. You drop to the underlying object, your functions give you functions. So this map, remember, is going to be F maps to some S of F. That is, if given a functor, you have a map on morphisms. So if you simply look at the underlying map on sets, that will also be injective. So in this context, I can of course define free objects. Okay, so suppose I take S a set. Okay, F in C. So what do I have? The free object, or more accurately, I should have said but uniqueness will be true in general. So I can say the free object on S, or generated by S in the category C is, first of all, it's an object F in C, and then of course S does not include in F. Instead, S includes in the underlying set of F. So you have an injective map into the underlying set of F. Okay. And such that for all, now I have to have another object, let's say A in C, and what we have is a map F, little f, which is going to map S not to A, which doesn't make sense, but instead to the underlying set of A. Okay. There exists a unique morphism, we'll call it phi, which is a morphism in the given category from F to A, such that the appropriate diagram commutes. Namely, I have A, I have sorry, it's not A to X, it's the other way around. I have F to A. Okay, this is a map. This will give you a map from S of F such that, well, let's first note what we have. So if I have, so phi will map A to, again the other way, F to A gives S of phi, which is going to map the underlying set of F to set of A. Okay, and what we know is that we have the commutative diagram. S is mapped by inclusion into S of F, the set of F, and it's mapped by F into the set of E, and the set induced map S of F phi commutes. Okay, so the corresponding map on set commutes. Okay, so what do we know? We know that free groups, well, we can see what we have. So examples. So we have seen free groups, Okay, how about free topological spaces? Free top. Well, this is, you can easily guess, it's just a discrete space. So unlike free groups, the free object is nothing interesting here. If you have a map on sets to another space, you get a map with so the same set with the discrete topology. Okay, and we also have free abelian groups. And examples of these are z to the n, and indeed if it's finitely many generators, so if S has mod n, then the free abelian group will be isomorphic to z to the n, and you can identify S with the canonical vectors it will be. Now I'm mentioning this because it could be slightly confusing, because after all abelian groups are groups, but remember the target we have is an arbitrary element in the object in the given category. So free group is not a free abelian group because it's not an abelian group at all, except for Z, which is the same in both cases. But the other way, the free abelian group is free in the category of abelian groups. That is, if I took any target abelian group A, and then I would get a map from Z to the n to A. So if I had again S included here, I would get this solution, but only if A was abelian. And if A was not, but on the other hand, the image of this under any homomorphism will have to commute. So if two elements generators went to elements that did not commute, you could not have such a map. So being a free object depends very much on what category you are. Okay, so you get a cheap example. So there are no free finite groups. I said cheap, it's not really obvious. If I restrict to just finite groups, then really when you try to construct a free object, you're forced to construct the whole free group, and that's not finite. So within the category of finite groups, also you can see there are no free fields. So free objects may not exist. So general cautionary principle when we are looking at categorical constructions, we do not always have them. In fact, fields are bad in many respects. We also don't have products of fields. I mean, we certainly can define products of fields, but they're rings, they're not fields. Okay, so this was just a digression, an overview on what free objects are in general.